Superposition. The superposition principle states that the voltage across or current through an element or device is the algebraic sum of voltages across or currents through that element due to each independent source acting alone. And that's quite a mouthful, and we'll learn this principle through examples. Now there are some steps that we can take to apply the concept of superposition, and the first one is to turn off or set to zero all the independent sources except one. Then you find the voltage or current that you're looking for, and then you repeat that for all the other independent sources. You turn one on at a time and the rest are set to zero. Find your voltage or current. Then we algebraically sum the results from the previous steps. Now, how do we set something equal to zero if it's a voltage source? Well, we short the positive and negative terminals of the voltage source together, and then we redraw the circuit. So if I want to find the response of R3's current and voltage just due to V1, I put a wire across V2, and now there's no potential difference because it's shorted, and node 2 is now at ground. I can redraw. There's no node 2 anymore, and R2 and R3 are in parallel. Now this wire that I'm putting here is really a mental model of what's going on. If this was a real circuit, I would have to take out this voltage source and replace it with a wire. So you might say, replace all voltage sources with a wire where it used to be. That's another way to look at it. But since we've been talking about shorting, that's why I chose this way. So now we can find the current through R3 or the voltage across R3 fairly easily. How do we do this with a current source? So I have two current sources here. They're independent, and I'm maybe looking for the current or the voltage across R1. So how do I set a current source equal to zero? I take it out of the circuit, and now there's no current flowing. It's an open circuit. And if there's no current flowing, that means there's no potential drop across R3. And in an interesting manner, node 2 and 3 become the same node. And so if node 2 and 3 are the same node, not because they're shorted, but because there's no current flowing through it, I can redraw it. And so now I just have R2 and R1 in series, and I can apply whatever I need to do to find the current and the voltage. Now let's do a more complex example, and I'm assuming you've done the examples in the book to lead you up to this. And this is a practical example, and it's an abstraction of a transistor circuit where I have a power supply, 5 volts. So this node here is at 5 volts, and it's going through a resistor. And I have Vout across RL, and I have this dependent current source, 10 milli scaled by Siemens times VG. So whatever VG is here, this current is 10 milli times that VG. And so this is independent too. And in time we'll see that this 1 volt can become a time varying signal. So let's analyze it. Well, LT-Spice can just calculate it all at once. .opt. And I just so you know, though, I changed 1 volt to 10 millivolts here, and I get Vout equals 0.363636 volts. Okay. Let's find Vout with VDD equal to 0. Okay. So I put a wire across this. Now it's shorted. So if it's shorted, I don't need it anymore, and I get rid of it. And there might be a confusion here to say, hey, I've shorted that voltage supply. If this is at 0 and this is at 0, then there must be no voltage across these resistors. But look at this, the way this wire is drawn. This is at ground, and this side is at ground, but out is not at ground. And if I twist this and redraw it, it's more easy to see that RL and R1 are in fact parallel. So that defines my current direction. So the current is going opposite to my voltage definition. So I get V out equals minus I times RL in parallel with R1. And that calculates out to be minus 0.09090909. That's because this is an inverting amplifier. Now let's find out what V out when V in is equal to 0. I put a wire across N, and now this Rn is shorted. And in fact, the gate voltage here is set to 0 because it's connected to 0. Now this has an interesting effect on the dependent current source, because if Vg is 0, it turns out that this dependent current source is also 0 as well. Well, how do we handle that? Well, we take it out of the circuit. And so if that's 0, there's no voltage here. That means this current source is 0. We take it out. And now look, V out is just the voltage division of R1 and RL. And we get 0.4545. So what's the total response? We add them together. And we get 0.3636, which is originally what we calculated.